Swayam Prabha. Digital India. Educated India.
Now, let us start our next module, that is we are starting module 7, dynamic soil structure interaction. Within this module, there are several sub topics has to be covered. So, let us start with the topic of dynamic earth pressures on retaining walls. So, why the computation of dynamic earth pressure on retaining walls are necessary? Just few introductory remarks, like design of retaining wall under seismic condition is very important in the earthquake prone areas to reduce the devastating effect of earthquake. So, evaluation of earth pressure under this seismic condition, which is nothing but giving a dynamic load, is important for such cases. And basically, we have several methods available to compute these dynamic earth pressures. Methods means analysis wise. So, analytical methods can be classified in broad two categories. What are those broad two categories? One is called force based analysis, another is called displacement based analysis. Okay? So, as the name suggests, in the force based analysis, we are considering mostly the forces acting at equilibrium conditions, limiting equilibrium conditions, etc., on the failure zone, on the wall, etc., to find out the what is the earth pressure acting on the wall, whether it is passive earth pressure, whether it is active earth pressure or earth pressure at rest. For different cases, we can get the through the force based analysis. Let us look at the slide. So, and in case of displacement based analysis, what is the difference? Based on the movements of the wall, how much earth pressures are going to generate, because we know the generation of earth pressures are functions of movements of the wall, right. If you remember the basic diagram, if I draw this for any rigid retaining wall, suppose we have backfill here and some backfill here, this is dredge level, this is the rigid retaining wall. So, for this rigid retaining wall, which is retaining backfill soil at this height at one end, other side at this end. So, this is the dredge level we are calling. So, depending on mode of movement of the wall, what we say, suppose this is the main backfill, if we say, if the wall displaces in this direction. So, movement direction if in this direction of the wall, then we say on this side active earth pressure is going to generate, on this side passive earth pressure is going to generate. So, basically this we called movement of wall, this is towards backfill, and this side we say away from backfill, and this is say earth pressure. So, typically we know the variation is something like this. So, this magnitude of earth pressure where there is no movement of the wall, that is this axis, will be nothing but P naught, that is earth pressure at rest. This magnitude of earth pressure after reaching the steady state, that value of earth pressure when the movement is towards backfill, this is we call passive earth pressure, and this magnitude of earth pressure when wall moves away from backfill is called active earth pressure. So, these are the three states of earth pressure we can have for a rigid retaining wall. For development of these magnitudes of earth pressure, as you see, some amount of displacement is required. Here we need this much amount of displacement delta A to have this full value of active earth pressure. For this also we need certain amount of displacement delta P to have this full value of passive earth pressure. If the wall does not move minimum this amount of movement, what will happen? The earth pressure is going to generate as partial, not full active or full passive. Suppose it move up to this, obviously we will get this much earth pressure, which is in between earth pressure at rest and earth pressure at active condition. Also, if the wall on this side moves up to this, the developed pressure will be something in between at earth pressure at rest and full passive earth pressure. So, these are called partial passive earth pressure zone and partial active earth pressure zone. So, that is why movement of wall is necessary, and beyond these values of course, it will lead to a failure condition after a certain displacement. And how to explain this theory using a simple Mohr circle? We know that a state of stresses for a small element, soil element, considering the principal plane for all these cases, that is, these are the principal stresses we are considering. Sigma v is vertical stress, sigma h is horizontal stress. So, at any particular point we are plotting shear stress versus normal stress for any soil element like this. So, sigma v, let us say sigma v is greater than sigma h at the starting condition. So, this is our sigma v and this is our sigma h. So, the Mohr circle will be something like this. This is at any state of earth pressure. Sigma h is nothing but the horizontal pressure which we can consider as earth pressure. Now, how to get the active state or passive state? Suppose if this is a C phi soil or phi soil, depending on that we will have, if it is a C phi soil, the Mohr Coulomb failure envelope will go like this. If we draw it on both the side, this is our phi friction angle of the soil and this is the intercept C cohesion of the soil. So, this is failure envelope. This Mohr Coulomb failure envelope, to generate the active state of earth pressure, wall is moving. Wall is moving away from backfill. When wall is moving away from backfill, obviously this sigma h is decreasing, right, because wall is moving away from backfill. So, sigma h is decreasing. So, what is happening? Sigma v remains constant, because there is no change in sigma v. What is happening? Sigma h is decreasing. Sigma h is decreasing as wall is moving. Sigma h is decreasing. Like that way, it reached a particular state when this portion touches the failure envelope. Am I right? So, it cannot go beyond this failure envelope, as we know. So, obviously, this is the minimum possible earth pressure, which is active earth pressure. So, this value will give us sigma A. This is the way we calculate the value of sigma A. And how to get the failure plane angles? If you join this with respect to this tangential point where the failure envelope goes through, that inclination will give you the inclination of your failure plane. Now, similarly, when the wall is moving towards the backfill, what is happening? Sigma h is keep on increasing. So, sigma h is keep on increasing. Again, remember sigma v remains same. There is no change in sigma v. So, what is happening? Sigma h is keep on increasing, 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 increasing. Okay. Sigma h is increasing, sigma v remains same here itself. So, when it touches this failure envelope once again, this is the value of maximum earth pressure, which is sigma p, which is called passive earth pressure. And that point, if you join with this failure envelope line, this is the inclination of your failure plane. These are the basics of finding out the earth pressure at active condition, at passive condition, and their corresponding failure plane inclinations. Now, these are by considering different amount of displacement, which can be classified as displacement based analysis, as I have mentioned here in this slide. So, for dynamic case also we can do either force based analysis or displacement based analysis. Let us see what are the common methods available in force based analysis. There are basically, if we can categorize them in three basic methods, there are several other methods, but these are the major three methods I can mention now: pseudostatic method, pseudodynamic method, and dynamic analysis using mass spring dashpot model. So, for our course on this soil dynamics, we will concentrate on this dynamic analysis using mass spring dashpot model. Other two methods generally we cover in other course on geotechnical earthquake engineering. Again, the sub classification within pseudostatic method, we can sub classify them as limit equilibrium method is one method, limit analysis is one method, method of characteristics is one method, and finite element method is one method. There are several researchers who have worked on these different methodologies to compute the seismic earth pressure using pseudostatic method. Using pseudodynamic method also there are several researchers who have worked on it and computed the seismic active and passive earth pressures on rigid retaining walls. Coming to dynamic analysis using mass spring dashpot model, what we have learnt in this course, researchers like Scott in 1973, he had proposed as a pioneering research in this using this model of mass spring dashpot, how to compute the seismic earth pressure or dynamic earth pressure on a retaining wall in the active case. Further, Veletsos and Yunan, they in 1994 computed the again active dynamic earth pressure on rigid retaining wall, and Chaudhary and Chatterjee in 2006, they computed using 2 degrees of freedom model. These two were the single degree of freedom model, and this was using the 2 degrees of freedom model of mass spring dashpot model, how to compute the dynamic earth pressure on wall. And in displacement based analysis also several researchers have done the work. I am not going into details of these things, because they come under the scope of another course. So, I will skip these methodologies. Also, the design guidelines as per the seismic design code of IS 1893, 1984 part 3 considers this earth pressure design. So, it is till 1984, other part 1 has been revised at 2002, other parts are still under revision, not yet come. So, how to compute the earth pressure? There are several guidelines like pseudostatic approach has to be followed, Mononobe-Okabe's equation has to be followed, and so on. Similarly, other design codes of Eurocode, the code followed in entire Europe, Eurocode 8 considers how to compute the dynamic earth pressure on rigid retaining wall. Now, coming to the model as we were discussing. So, dynamic analysis of rigid retaining wall using mass spring dashpot model. If we draw the typical picture, this is the rigid retaining wall and this is the entire backfill. We are considering simple vertical face retaining wall and a horizontal backfill, and different excitations of dynamic load we can apply here at the base of it. So, this is the acceleration we are applying x g double dot. This was considered by Chaudhary and Chatterjee in 2006. Similar model was taken by the pioneering work, as I have mentioned, by Scott in 1973. That was basic single degree of freedom model. What Scott considered, this is the rigid retaining wall, the point of application H e at the height of H e from the base of the wall, and wall is shaken with this amount of acceleration, ground acceleration, and the soil, this backfill soil has been modeled as the stiffness and damper material. Okay? And m is the mass of this wall. Fine. So, that was the model considered, the single degree of freedom model, mass, spring and dashpot with 1 degree of freedom. That is the movement of this one, right? Movement of the wall, how much it is moving. Veletsas and Unan also had considered the similar way. So, it has been considered like this: wall is moving by amount x. So, basic governing equation of motion can be written like this: m x double dot plus that damper of the soil times velocity plus stiffness of the soil times displacement will give us mass times whatever is the base acceleration. This expression actually we have seen for the case of earthquake analysis of frames also in the very beginning, how to model them, right. And how to get the magnitude of the earth pressure, the magnitude of earth pressure, that is why this mod is used, Q B is called, which is nothing but, if you look back the single degree of freedom model once again, how much pressure is acting on this wall or how much force, earth pressure force is acting on this wall, that is the force generated from this spring and force generated from this damper will be nothing but the force acting on the wall. So, that is why this stiffness times displacement plus the damper times velocity will give us the value of the how much dynamic earth pressure is acting on the wall. And how to compute this stiffness? The expression to compute the stiffness is given here, which is given in Veletsas and Unan and used by Chaudhary and Chatterjee also. Where from this expression has come? If we remember the value, how we got this expression for k, the k is nothing but m omega square. Am I right? So, omega is given by this expression, omega is given as pi V s by 2 h is the expression to compute the omega natural frequency, and this V s is nothing but root over g by rho 2 h. Hence, k can be written as m omega square. So, this becomes pi square by 4 h square times g by rho. That is the expression to be used to calculate the value of k. So, the same expression is given here also, if we look at the slide. Now, modifying that single degree of freedom model, Chaudhary and Chatterjee, this is the reference in the journal Sadhana, that is Proceedings of Engineering Sciences, Springer journal publication in 2006, volume 31, number 6, page 1 to 10. it proposed instead of considering a single degree of model, it should be considered as 2 degree of freedom model, 2 degree of freedom model. Why? This is the wall, rigid wall, this is the mass of the soil which is participating during the failure of the wall. Okay. So, that is why the soil and wall, they have different properties, of course. So, it should be considered as 2 degree of freedom model, considering the mass of wall from wall properties to get the damping constant and stiffness for the wall. So, C2 and K2 are correspondingly damping constant and spring constant of the wall. M1 is the mass of the soil which is participating, and C1 and K1 are the soil damping and soil stiffness. And this F1T and F2T, what are these things? These are applied dynamic load. These can be computed from this xg double dot. So, looking at this, which is quite logical, because at the end we are considering it as rigid or fixed, because at large extent in the horizontal direction, at far field no effect will be there. So, that is why we have to now understand how to calculate this M1, that is zone of influence has to be considered. So, considering this basic 2 degrees of freedom model, what was done? The free body diagram of mass, free body diagram of mass M1 and free body diagram of mass M2. M2 is nothing but wall. So, on wall we have externally applied dynamic load F2T, the damper force will be C2 times the relative velocity between the two, that is x2 dot minus x1 dot. Why it is 2 degrees of freedom? Once again let me tell you, these are 2 degrees of freedom. X1t is the movement of the soil, x2t is the movement of the wall, and stiffness force will be the relative displacement between the two. So, K2 times x2 minus x1, and the inertia force will be m2 times x2 double dot. These will act in this direction, because we have considered our x2t in this direction. So, obviously, at an instant of time, all these are resistive force acting in the other direction, right. Now, for mass M1, that is on soil, what are the things acting? On this side we have the damper force C1 x1 dot, we have spring force K1 x1, we have inertia force M1 x1 double dot, and the balancing this damper and spring force, we have C2 times x2 dot minus x1 dot in this direction, because here it is in this direction, and this force will be K2 times x2 minus x1 in this direction, whereas here it is in this direction. So, these will be internal forces balancing each other, and F1T, the externally applied dynamic load on this component, will be acting in this direction. Fine. So, with this basic model, it can be further extended to compute the dynamic earth pressure acting on the wall. Now, just a brief about the basic pseudostatic method of analysis using limit equilibrium method, as was proposed by the first work done by Mononobe Okabe, as I said, which is known as Mononobe Okabe method of computation of seismic active as well as passive earth pressure. This is the line diagram of a rigid retaining wall, which is retaining a backfill soil up to this height at one end, and on the other side the height of the soil is at this up to this level. So, considering the wall movement occurring from left to right in this direction, what we can say, active state of earth pressure is going to get generated on this side, whereas on the other side where the wall is moving towards the backfill, we can have the passive state of earth pressure getting generated. So, these two generation of state of earth pressure we had discussed already, how they are going to occur. This is because of changing of the value of the horizontal stress condition. The vertical stress remains same. And then considering the more Coulomb failure theory, when it reaches to the failure state, then we consider full active earth pressure and full passive earth pressure has been developed. So, that is why in limit equilibrium method, it is quite correct to assume some kind of failure surface, because we are handling the condition at the state of failure. So, that is why this different failure surface can be assumed by different researchers. Mononobe Okabe had proposed to assume planar failure surface like this for both active as well as for passive case of earth pressure, dynamic earth pressure, and earthquake accelerations were mentioned like this AH as horizontal seismic acceleration, with which can be represented by this KHG. KH is nothing but coefficient of horizontal seismic acceleration, and G is obviously acceleration due to gravity. Similarly, AV is considered as vertical seismic acceleration, which can be expressed as kV times G, where kV is called the coefficient of vertical seismic acceleration. Now, as the method suggests, it is a pseudostatic or quasi-static method. So, along with the static forces acting on this failure wedge, we know how to analyze the failure wedge to compute the earth pressure acting on a retaining wall from Coulomb's theory. So, Mononobe Okabe theory is basically the extension of Coulomb's earth pressure theory in the case of static loading. So, in Coulomb's earth pressure theory, whatever forces were acting, they considered cohesionless soil. So, obviously, three forces were acting: weight of this failure wedge, then this active earth pressure which is getting generated, and the soil reaction coming from this side. So, these three forces has to be in equilibrium and they will meet at one point. So, the force triangle has to be satisfied at equilibrium condition. Now, in case of pseudostatic analysis, what are the extra forces coming into picture? These two extra forces, that is the horizontal inertia force because of this horizontal seismic acceleration. So, kh times the weight of this failure wedge, kh times w is nothing but horizontal inertia force, and the vertical inertia force is nothing but kV times w, which will act in the vertical direction. Remember, being these are earthquake accelerations coming out from the earthquake acceleration, they can act in both the directions, that is from left to right as well as from right to left. Also, this kVw can act in both the direction, towards upward and towards downward. Now, among these four combinations, because if you take these two forces, then obviously considering two directions for each of them, we can get four combinations, right. So, among those four combinations, we are supposed to find out which one is the critical combination which is giving us the design active earth pressure. And what is design active earth pressure? We know from the Coulomb earth pressure theory, what we do to find out the active earth pressure, we consider different failure surfaces at different angle of inclination with respect to horizontal, and then we optimize or maximize the active earth pressure with respect to this angle. That is the methodology we adopt in Coulomb's earth pressure theory. So, in this case, along with this optimization, we have to do one more optimization additional, that is involved with these four combinations of the seismic forces. So, the combination which will give us maximum value of this PAE, that is active earth pressure under earthquake condition, will give us the design value of seismic active earth pressure. Okay. Similarly, if we talk about the passive earth pressure, what we do in the case of passive analysis, in Coulomb's theory, when there is only static forces are involved, three forces will be there for cohesionless soil, weight of this wedge, soil reaction, and this passive earth pressure getting generated. So, we use different angles for this different planar failure surface, and then we optimize, means in this case of passive we minimize the value, because this passive is the resistance. So, get a design value, we have to minimize the value of passive earth pressure, which will be the design value. And then in the case of seismic forces, what we are involved here, additional 2 forces similar to this with 4 different combinations. So, these 2 seismic inertia forces will come into picture, and among those again we have to do 2 optimizations, one with respect to this failure angle, another with respect to the direction of the combinations of the seismic forces acting on this failure zone. That will give us the absolute minimum value of this PPE, which will be the design seismic passive earth resistance. This is sometimes called passive earth resistance, because it is truly speaking is not the pressure acting on the wall, but it is the resistance offered by the soil to the wall. So, this was the basic equation proposed by Mononobe Okabe. You can see this is nothing but Coulomb's equation with an additional term of this portion, which considers the earthquake acceleration in vertical direction also. And the equation closed form solution for this coefficient of active and coefficient of passive seismic earth pressure is expressed by this equation, where different parameters I can mention. Here beta is nothing but angle of inclination with respect to vertical, the face of the wall. I is the angle here for the backfill soil, and delta is the wall friction angle. You can see here this is delta, and phi is friction angle, soil friction angle, and theta is another angle which can be estimated by using this relation of tan inverse kh by 1 minus kV. It satisfies actually the criteria of shear fluidization. If you remember, we talked about during the chapter or during the module when we discussed about liquefaction of soil to take care of the stability of the soil. This is the criteria we have to satisfy. So, from that criteria this theta comes, and for stability phi should be greater than this theta, that is soil friction angle should be greater than this theta. Then how the pseudodynamic method was proposed, means the changes from the pseudostatic method are like this. Here the shear wave and primary wave which are travelling during the process of any earthquake are also considered effect of them, and this QH, QV are the horizontal and vertical inertia forces which can be calculated based on the variation of the earthquake acceleration with respect to depth, also with respect to time, and by considering the frequency content of the considered earthquake. So, that is why as I said, all the dynamic nature of earthquake forces can be considered in this pseudodynamic method. Hence, instead of considering a single coefficient or single value attached to the weight of this failure zone, it is considered as infinitesimal small element or specimen at any depth z with a height or thickness of dz, and that on that element we have considered how the acceleration in both vertical and horizontal direction they are creating the inertia forces, and those inertia forces are further integrated over the entire height of the wall. So, these are some of the expressions how the horizontal seismic acceleration is approximated. It will be obviously random in nature, but for obtaining a closed form solution we need to consider some equivalent form of the equation, so that it leads to a generalized solution which can give us a design chart. So, that is why any random motion we can approximate by considering the area under the curve and different methodologies. That equivalent sinusoidal wave was considered in or was assumed. H is the amplitude of that motion, omega is the frequency of the earthquake, h is total height which we are considering for the height of the wall, z at a particular height where we are considering for that infinitesimal element, and t is the time for which the earthquake is occurring, the duration of earthquake, and V s is shear wave velocity which is creating, we have assumed that V s is creating the horizontal acceleration, and Vp, that is primary wave, is creating the vertical acceleration. These also I have discussed what type of direction of excitation out to the particles these different waves generate in the module of wave propagation. So, similarly, the vertical acceleration is expressed in this way, and the inertia force in horizontal and vertical directions are nothing but mass of that slice times acceleration. Mass times acceleration will give us the force. So, that is inertia force. We have to integrate it over the height of the wall, and then we will get different expressions and solution. Finally, we used limit equilibrium method to get the expression for PAE, and remember this needs to be optimized with respect to the different failure plane and different combinations of these directions of QH, QV. And what the design code mentions, the IS code, Indian Design Standard IS 1893 seismic design code. The part 3 handles the portion about this bridge and retaining wall under seismic condition. It is 1984 version, as I mentioned, that IS 1893 part 1 has been revised in 2002, but other parts are still under revision. It has not yet come out. So, what it says that using pseudostatic approach, we can evaluate the stability of retaining wall by considering the seismic earth pressure. So, it proposed to use the Mononobe-Okabe equations. Dynamic increment of earth pressure will act at mid height of the wall, and effect of dry, partially submerged and saturated backfill is considered, and range of permissible displacement is not specified in the code. So, there are several drawbacks, as you can see, and approximations as in this code, because it was framed and came out long back. So, after that several research output and advancement has taken care of, and that is why different country seismic codes have been revised, but Indian code are still under revision. So, hopefully, it will also come out with some good guidelines. And as per Europe code, Eurocode 8, that is also based on pseudostatic analysis, but the beauty of this Eurocode, they considered the Richard-Elms model to take care of the displacement also. So, which is very important, we should know how much displacement we should allow. So, that this is based on the displacement based criteria. So, permissible displacement for sliding as well as rocking movement of the wall have been considered in this, and it includes the nonlinear behavior of the soil and backfill also. So, which is another advancement, and the point of application of dynamic earth pressure, it still considered at mid height, and different hydrodynamic force if it is a saturated layer is assumed is mentioned in this code. Eurocode 8 also they had 1998 version, later on they revised in 2003. So, like that frequently they revise their code as per the research developments keep on going across the world. Similarly, the NIHARP code is available for US, and UBC is also available for US. Those are also considering, mostly NIHARP is considering most geological guidelines, and NIHARP code 2003 is probably the latest one. So, that considers all the effects of permissible displacement of the wall under seismic conditions and different calculation methodologies for earth pressure. And one extra important thing I forgot to mention, in Eurocode 8, they mentioned to calculate the soil amplification also, which is absent in the Indian standard code. So, soil amplification during the earthquake process, the amplification factor, it can be considered in our pseudodynamic analysis, whereas in pseudostatic analysis there is no scope for considering the amplification as such. Now, coming to the methodology which is involved for our course, that is dynamic analysis using mass spring dashpot model. This is the basic model we had considered by Chaudhary and Chatterjee in 2006, the rigid retaining wall schematic diagram, and this is the backfill soil zone which is getting excited under some dynamic loading. And what was the basic model proposed by Scott in 1973? He considered single degree of freedom mass spring dashpot model instead of 2 degrees of freedom. He considered this is the rigid wall and this is the excitation. It was equivalent model with by considering this effect of the soil was taken by using a spring and dashpot. That is, soil was replaced fully by a spring and a dashpot, and that was considered to be attached with the wall, and wall mass was considered in that single degree of freedom model for this retaining wall. Also, this model was continued and followed by Veletsas and Yunan in 1994, and they used better expressions to compute the stiffness values for soil involved in this basic governing equation for single degree of freedom, and how to compute the magnitude of earth pressure. They also came out with that magnitude of earth pressure acting on the wall is nothing but coming from this spring force and the damper force. But always it can be questioned whether the mass of the soil is only involved in this process of dynamic analysis, or mass of the soil also should be involved, because in our other analysis, when we do any limit equilibrium analysis or limit analysis as such for earth pressure calculation, we take the zone of failure within the soil mass, and both of them are experiencing through the earthquake forces, and that has to be considered. Its effect also has to be considered, which is directly coming on the wall. So, that is why further modification was done by this work of Chaudhary and Chatterjee. This wall has been modeled as M2 mass of the wall, and wall properties mostly for concrete or RCC wall or whatever different types of wall material you use, depending on that damping constant and the spring constant can be evaluated, and M1 is the mass of the soil involved taking part into the analysis, or which is taking dynamically vibrated along with the wall, and the soil stiffness and soil damping has been also considered. Now, if we draw the free body diagram of each of these mass, that is the M1 is for wall, M2 is for soil, we can easily see that this is the boundary has been considered as rigid, because at far field condition we can always consider it as a rigid boundary. These are the forces: externally applied dynamic load, inertia force, these are the damper force and spring force. These two are the balancing forces between the two material, and this M2 X2 is nothing but the wall inertia force, right. So, M2 is for wall and M1 is for soil. So, this is for soil and this is for wall, and F2T. Now, in this case, the question automatically arises, we can easily compute M2, because for a chosen wall section which we are going to design, or suppose we have designed considering the static loading for all stability, we know the section of the wall. So, M2 can be calculated, and that we can do the dynamic analysis and see how it performs in terms of its displacements, etc., whether it is within permissible limit, that can be checked. So, we do not have any doubt about M2. What about the other parameters? How to compute K2, C2, these parameters? Let us go back to the expression of this K. K is given by this M times pi square by 4h square times G by rho. M of the corresponding material for which we are calculating, suppose K of wall we want to compute. So, here M of the wall has to be considered, H is the height of the wall, G is the shear modulus of the wall material. So, for concrete, if you are using the concrete wall, then concrete shear modulus has to be used, and rho is the density of the wall material. So, rho of wall material has to be used in the expression. What about C? How to calculate the C? Damping, this is 2 eta root over K m. Do you agree with me? That is the expression we know, the standard expression, that damping constant can be estimated using damping ratio, stiffness and mass. So, for the estimation of damping constant of concrete or wall material, we should know the damping ratio of the concrete. So, damping ratio of the concrete is more or less known, mostly it is about 5%. So, 5% if you consider the damping ratio, K just now we have estimated, M of the wall also we can calculate. So, C of the wall will be known to us. Okay? So, this way we can estimate M2, C2, K2, which is fine. Now, the question comes, what way we can calculate M1, C1 and K1. Expressions are available, but the first thing we should calculate is M1. That is why Scott avoided probably the calculation of M1, because this is not so clear. So, how to get the value of M1? For that, what is required? We should know what is the influence zone. How we can do? In this paper, what we have done the analysis, we have considered different distances. This horizontal distance we have considered in terms of some factors of this height h. Suppose 2 h, 3 h, 5 h up to 10 h, and we have done a trial and error process of analysis by using different zone of extension and tried to obtain the final output of the displacement function. And when after a particular distance, horizontal distance, we found that there is hardly any change, significant change in the value of the displacement function, what we can say that beyond that it is hardly having any effect on the wall. So, that is nothing but the way to compute the zone of influence for the estimation of this soil mass. Clear? So, if you go through this paper, which I have already given the reference, this is the paper, you will get all the details, and that way finally, we have found out for different conditions of course, applied forces, dynamic forces, what are the different zone of influence. And from that, now we are ready to calculate M1 very easily, because it is a simple rectangular area we have considered in this figure in our basic model. Height is known, this influence zone is also now known, and other dimension is per meter always we consider for retaining wall plane strain problem. So, the total volume is known and soil density you know. So, unit weight you know. So, you can find out easily the mass of the soil. So, M1 is known. Once M1 is known, now we are ready to calculate K1 also, that is spring constant for the soil using this expression. So, here M1 is now we have calculated, H is known, G of soil has to be used here and rho of soil has to be used in this expression. And then coming to the calculation of C1, that is for soil damping constant, again we refer to this equation. Here eta damping ratio of the soil should be known to us, that in our analysis we have varied for different damping ratio. You can easily get a design chart for different damping ratio or different types of soil. We have considered 5%, 10% and 20% damping ratio, which are the practical ranges of different damping ratio for the soil material, as we had discussed earlier also. K already we have computed K1, and this will be M1, that also we have calculated. So, we can get C1 very easily. Fine. So, with this knowledge, now next step, after considering this free body diagram, we can easily write down the, by applying D'Alembert's principle, what are the equations, and those governing equation of motion for 2 degree of freedom model in matrix form we can express in this format. Am I right? Because it is a 2 degrees of freedom system. So, in matrix form x1 and x2 we need to determine, and that way we have, and dynamic active earth pressure on the wall has to be calculated based on QB will be, remember QB is nothing but on this whatever forces are coming, these forces, that is inertia force, stiffness force and the damper force, some of them will be nothing but the force acting on the wall, which is in horizontal direction nothing but the dynamic earth pressure, right. So, that way QB we had estimated, and then the non-dimensional dynamic earth pressure is plotted in this result, non-dimensional active earth pressure, dynamic active earth pressure with respect to different frequency ratio. Different frequency ratio in this case, which frequency ratio we have considered? This omega is obviously the exciting frequency or applied frequency, different excitation you can consider always, and omega 1 is the natural frequency of the soil wall system, considering how many natural frequency we will get here? We have considered 2 degrees of freedom system. So, obviously, we will get 2 natural frequencies. Now, among them, which natural frequency we should use? The fundamental natural frequency. What is fundamental natural frequency? Among the 2 natural frequency, whichever is the lowest one, that is the fundamental natural frequency. So, by considering that fundamental natural frequency, why it is required to consider? It will give us the first mode shape, right. So, in that way the frequency ratio we had calculated here, and how the earth pressure force, dynamic earth pressure force is non-dimensionalized. It is the value of q b mod of that divided by rho x double dot g. X double dot g is the applied ground acceleration, that is for a particular dynamic force or a earthquake force, whatever accelerations we had considered, and h square. So, obviously, this unit and this unit will be same. So, we can get a non-dimensional value. This is also non-dimensional. For different damping ratio of soil of 5%, 10%, 20%, you can see the variation is something like this. So, it is kind of a design chart, because once you know for your soil wall system what is the fundamental natural frequency, and also the zone for which you are going to design, or the dynamic load for which you are going to design your wall, the exciting frequency will be known. So, this value will be known to you. You can go to this chart knowing this damping ratio, you can get a value of this. In this, rho x g double dot and h square also will be known. So, you can get the estimation of this q b. And also how to validate the model? We have validated our model with respect to basic single degree of freedom model of Scott's model. You can see this is our proposed model considering 2 degrees of freedom model, and this one is Scott's model by considering single degree of freedom model. You can see at higher frequency ratio, Scott model or single degree of freedom model is giving a drastic change in the result, whereas 2 degree of freedom model can replicate a smooth curve or smooth results, which is expected actually, the variation of the results of this dynamic earth pressure with respect to different frequency ratio. Otherwise, at the close to the resonance condition, they are matching pretty well. However, at higher frequency ratio, 2 degree of freedom model is capturing the better behavior or better result or better response of the wall than a single degree of freedom model. We will stop our lecture here today. We will continue further in the next lecture.